Hi, we continue section 7.1, one-way analysis of variance. So last time that we did define the one-way layout and that we did the analysis of variance. So that can test if multiple groups are all the same or different. So we have for example, the three groups, the 1, 2, 3, and the null hypothesis is that all groups are the same, and alternative, the some groups are different. But such a hypothesis that all groups are the same is, if the hypothesis is rejected, it's not easy to interpret because we don't know which group is different from another. So overall, it's different, but 1 and 2 are different, or 2 and 3 are different, or 1 and 3, or all similar, but the overall, it's the different. So it's not clear what it means. So a clearer way to test is the pairwise comparison. So it's a little more complicated, but at least it's much easier to interpret. 1 versus 2, 2 versus 3, and 1 versus 3. So that we try this, and there are several functions to do this conveniently. So for just demonstration purpose, that we pick the first 6 observations of Setosa species in iris dataset, and the first 8 observations in Versailles color, and the first 10 from Virginica. Because if we use 50 observations, the difference is so clear, so that we just picked a few observations from them. So this is the dataset to use. Then, so this is the box plot for the sepal lengths of these 3 species. Sepal lengths. So you can see this is clearly, Setosa is clearly smaller than Versailles color, but the Versailles color and the Virginica, it's somewhat similar. Okay, so this is the pairwise, the test result. So we compare pairwise. So Setosa versus the Versailles color, Setosa versus Virginica, and the Versailles color versus Virginica. So we have 3. And these are p-values, 0.00398. So it's highly significant, less than 0.05. So these are p-values. And this is also significant, 0.00017, the Versailles, Virginica, and the Setosa. Actually, the difference is larger in the previous box plot. Versailles color and Virginica, the difference is not significant because the p-value is more than 0.05. And you can see a large overlap between these 2 groups. And if we, and this is done by the pairwise t.test function, pairwise.t.test function, and you put just the sepal length, the variable, and the species, and this is the definition of groups. This defines groups, and I will explain this later. And you can get this at once. But we have studied t-test before in chapter 5. So if we use just the 2 vectors, we put 2 vectors, you can compare the 2 groups. So in that way, that we can also test the pairwise difference. So this is the Setosa versus Versailles color, Setosa versus Virginica, and Versailles color versus Virginica. And the p-values are obtained here. And these are actually similar, but slightly different. So the first one, for example, Setosa versus Versailles color. So last time that was 0.00398. So 0.00398. So it's not terribly different. So you can see this one and this one are kind of close in the sense, at least in terms of the size, the order of the size, but not exactly the same. And these 2 are similar. For example, this was 0.21, so it's similar, but still different. And what makes the difference? Our code is not correct? Not really, but we have different assumptions. At first, the t-test function we used here, we just do 3 independent tests. So we estimate the size of sigma for each pair. So at first, we estimated the sigma, the size of sigma, using these two groups. But the second test, we used these two groups, so Seto-signed Varshiniker, sorry. And the third group also, we only used the Varshiniker and Varshiniker to estimate sigma. But pairwise .t.test function estimates sigma with all three groups. So just from all three groups, we calculate sigma, but to compare, we only use two groups. So that difference in assumption that makes p-values different. And if we want to get the same result from this pairwise .t.test function, then you can specify the pool.sd is equal to f, false. So which is appropriate? So it really depends. So the pairwise t.test function estimate is just one sigma. It's a kind of easier to interpret, but which is more accurate, it really depends on the situation, and we cannot really say. Yeah, and next one, okay, so we did multiple tests. And if we use usual p-values, then we have some trouble. Because if we have multiple tests, it's more likely that the sum of the tests reject null hypothesis. For example, if we think about the 7 groups and we do pairwise t-test, how many combinations? That is the 7 choose 2. So that is 7 times 7 minus 1 divided by 2. So in total, we have 21 tests. So if we have the significance level of 5% for p-values, we have 21 tests. So on average, 21 times 0.05. So on average, 1.05. So one of them are just, by chance, reject H naught. That is our expectation. So that is problematic. So everything is just, okay, so basically 7 groups just come from the same population. But still, if we do all pairwise tests, on average, we reject the one null hypothesis. So that is a problem. So we have to adjust p-value. We have to get more strict the rule to reject null hypothesis. So if we have the k independent tests, then to have overall the significance level of alpha, we have to set the threshold for p-value at theta, such that 1 minus theta to the kth power is equal to 1 minus alpha. So in this case, the entire probability that we can reject at least one H naught is equal to 1 minus alpha. And okay, so how about the approximate size of theta? So approximately theta is alpha over k. For example, if we have the threshold at the p-value at 0.025 and we do 2 tests, basically we have about 5% probability to reject either of the null hypotheses. So approximately we have to set theta is equal to alpha over k, and this is called the Bonferronius method. So this is very rough approximation, but still the statisticians are rough, so we use this. So now that we don't have to reject too many null hypotheses. And you can do this adjustment by specifying the p.adj is equal to the Bonferroni in pairwise t.test function. And actually, these p-values are 3 times as large as the previous one. So last time that we have 0.00398 or something, and this becomes this. So still, it's significant at 5% level. But if original one is very close to 5%, then it becomes insignificant if we use this adjustment. Yeah, so this is the pairwise tests and how to deal with the multiple tests. So often the multiple testing problem is ignored in many of the statistical analysis. So we have to be careful about it.